G'day guys, and welcome to our lesson on power generators. Now if you've seen the video on motors, you recognize the setup here. And in fact, the setup for a motor and a generator is very similar. Both have a coil sitting between the north pole of one magnet and the south pole of another. So magnetic field lines going that way. But they differ in that in a motor, we supply the current. So we pump a current through this coil, like that. And moving charges in a magnetic field experience a force given by the right hand slap rule, thumb in the direction of current, fingers in the direction of the magnetic field lines. If that's your right hand, your palm should be up. So you see a force that way, and the motor turns over there. That coil will turn on that axis with the green dotted line. A generator is different. In a generator, we don't supply the current, we supply the force on this coil. So we supply that force ourselves and force the coil or the loop, I'll use the term loop, so it's just one wire, loop to turn around. So if we apply that force, the next picture of that loop we'll see is it tilted up here at 45-degree angle, like that, and we'll continue to supply force, bringing it over like that. So in a motor, the moving charges experience the force. In a generator, we physically pull that loop around. And by doing that, we change the flux through the loop, and therefore we can generate a voltage. That last little bit there is given in Faraday's law here, where it says if you have a loop, the voltage you're producing in that loop is equivalent to the number of wires in that loop. So if I'm using the term loop, it's 1, so n equals 1 for a loop, multiplied by the change in flux over the change in time. And the flux is given by that magnetic field strength, or the strength of the magnetic field, dot product with the area. And the dot product simply says if the area here is at right angles to the magnetic field, you will get a flux. If the area, say this loop along the plane of the page here, is parallel with the magnetic field, you will not get any flux. The flux will be 0. And that dot product here, the fact that it's not just any B, any magnetic field strength times any area, allows us to exploit the position of the area, the orientation of the area. So instead of changing the area, actually making the area bigger or smaller, we just change the angle between the area and the magnetic field. Let me explain what I mean by that. Oh, and the final thing is Lenz's law, which states that the current induced in a loop or wire will oppose the change in flux. And we'll use the right-hand grip rule to determine the direction of the current flow. So going back to these pictures down here, the first image of the motor, if we push it this way, and we end up with a motor tilted up as we saw before. If the magnetic field lines here are running parallel to the area, pretend they're just scraping the surface of these two wires here, the flux for this first picture is equal to 0. Or in other words, that area in the loop doesn't collect any of those magnetic field lines. However, when it is orientated like this, it will start to collect some of those magnetic field lines. So imagine this is a 3D space. You can see how some of these magnetic field lines are now passing through. This is lifted up and allowed them to slip under. If it is now collecting those magnetic field lines, the area along this plane is no longer parallel to the magnetic field line, so we will start getting a flux because we have both magnetic field strength and area. So we'll say here the flux is medium strength. And the reason it's medium strength is because first of all it's not 0, but secondly we can see we're not collecting as many magnetic field lines as we could. It'd be like if those magnetic field lines were butterflies, and this were a net with which you were catching the butterflies. This orientation of the net creates quite a small opening for those butterflies to enter. You get the feeling if you just twisted your hand around a little and orientated this more vertically, you'd be able to collect more butterflies, and if our analogy is correct, to collect more magnetic field lines. That's why we keep pulling the coil, the loop around, and we end up with this, a loop whose face, whose area, is perpendicular to those magnetic field lines. So this is the point where we have the maximum flux passing through this loop here. If we then continue to pull that loop around, we get something like this. I'll try to... There we go. So this top here is gone down there. And notice especially this part of the wire has become that part of the wire there. It's moved over like that. And the flux we see now is not as high as it used to be, because we can collect only a few magnetic field lines in this orientation compared to this orientation. It's about on par with this configuration here. So we've got flux down to medium again. Let's use, actually first of all we'll graph the change in flux over the change in time. Time, flux. So we said the flux was 0 here, medium here, max here, and medium here again. And if we extrapolate this line, we see it is sinusoidal. Or is that sinusoidal? It's spelled funny. And it actually looks like that. And the reason we get negative flux is as this loop goes around past, say, this point here, now the flux is coming through effectively the back of the loop. So it used to come through, we'll say, that side under there was the front of the loop. Now it's coming through the back of the loop, so we're saying the flux is negative. And if the voltage is equivalent to N, which here is 1, delta flux over delta T, well, this is the gradient of this line, then the voltage is equal to, the gradient here is 1, here is 0, here is 0, here is negative 1, so that there is a graph of our voltage. So that's EMF, electromotive force, and that's the voltage there. This indicates to us, since the voltage is positive here and negative here, it's hinting, oh no, I've got those the wrong way around. This would be the EMF. Oops, no. Sorry, this is the flux, and this is the EMF. Since the EMF is positive here and negative here, it's telling us the voltage must reverse direction. Yet let's use Lenz's law to determine the direction of voltage, the direction of current, and whether the voltage is positive or negative at all these different points here. So first point, well, there's no flux, so we're going to have to look at this point here. The flux has increased this way through the loop. Lenz's law states that a current will be induced to oppose that change in flux. So we want current to be induced, which will push flux this way through the loop. Using our right hand grip rule, so we put our thumb in the direction of current and we curl our fingers around the loop. You see that if the current ran this way, you'd be pumping flux that way through the loop. But if the current ran that way there, you'd create some flux or some magnetic field which would oppose the change in flux. So we want the current to run that way around the loop. As we go from this picture to this picture, well, we said here the flux was only medium strength, and as we turn the loop perpendicular, the face of the loop perpendicular to those magnetic field lines, we're actually increasing the flux even more. So we want to induce a current which will again force magnetic field lines that way, and the way to do that is to push a current this way through the loop. So the induced current is that way there, and since this loop is moving, we know that the current is also that way there. The really interesting thing occurs here. As the loop turns over, remember we said this wire here becomes this wire here, it sort of pushes over like that. Well, the amount of flux through the loop is decreasing, because here it was full on perpendicular, we collected all those butterflies or all those magnetic field lines, but here it's collecting only a few. Because of that, we want to push more magnetic field lines this way to oppose the reduction in flux. And you can see, if you want to do that, put your thumb in the direction of the current you're guessing, and you'll curl your fingers below under there, and you'll see that you want current to flow this way if you want to push magnetic field lines through that way. So if it's this way here, you can place your thumb anywhere on that circuit. Whoops, got those the wrong way. There we go. Notice, in this picture here, this part of the wire was where the current was flowing into the loop. In this picture here, the current is flowing out of the loop. So here's the key part to remember. As the loop passes that perpendicular orientation here, the direction of the current will change. The voltage will go from positive to negative. So filling in the rest of the current up here, in there, out here, in there, out here, in there, out here, and then all of a sudden, since we're focusing on this wire here, it's out of that same wire and into the wire that was under here. A lot of people get confused because they fail to take into account the fact that this wire has now moved over and is now that same wire there. So the direction of the current swaps when it's at that vertical orientation there. If we had slip rings, and slip rings basically say we have a circuit built around the motor, and this wire of the circuit will only connect to one wire of the coil at all times. So say this wire here connected to that one there, it would connect to that one there, and that one there. So even though it's rolling around, the slip ring assures it only ever connects to this end of the circuit, and this wire will connect to this wire, therefore this wire, and this wire. That's slip rings. If we had a split ring commutator, it means that this end of the circuit would connect to this wire here, this wire here, this wire here, and then swap over to that wire there, therefore assuring that current is always being pulled out of the circuit that way, because as you can see, it's being pulled out of the circuit there, and there. If the current is always flowing out of this circuit one way, a split ring commutator will have a current through this resistor looking like this, kind of like a full wave rectified AC, and a slip ring commutator will have a current through this resistor looking like this. So we'd get both positive and negative direction of current. So the last thing I want to do is solve a question using the formula that I've introduced, Faraday's law, up here. So say I had a motor and the coil was sitting between a north and a south pole, the magnetic field running across there, was equal to 2 Tesla. This length here was 3 meters. This length here was 6 meters. And if it will say it's a loop, so n equals 1. And it's spinning. The total time it takes to complete one revolution is 16 seconds. So one full revolution like that. Let's figure out the average voltage being induced in this wire here. So first of all, we pick 2 points which the loop could sit in. The first one I've drawn in blue, and the second one in green. So you can see how that loop would move up like that. In the first case, the flux initially was 0 because the area is parallel to those field lines. In the second case, the flux is a maximum. So we'd see a lot of field lines passing through that area. And the flux finally was equal to BA. Since it is at 90 degrees, we can just multiply B by A. And we get 2 times, and the area was 6 times 3, it's a square. So 2 times 18, or 36 Webers. And since it's delta flux, that's the change in flux, delta flux equals 36, take 0, or 36 Webers. Now, how long did it take the loop to get from this point to this point here? Well, if it took 16 seconds to complete one full revolution, and this is a quarter of a revolution, then the average EMF produced in this time here will have been produced over a time of a quarter of 16. So EMF equals N1 times delta phi, that's 36, over, so 16 seconds for one full revolution, therefore 4 seconds for one quarter revolution, which is equal to 9 volts. It's actually quite difficult. This is a huge loop, you can see, 6 meters times 3 meters. It's quite difficult to get a loop big enough to produce even a negligible amount of voltage. The easy solution, therefore, is to either spin the loop very, very fast and make delta T very small, or to make not a loop between two magnets, but a coil, which means, I'll draw it in yellow, we run a wire around and then keep that wire going around, going around, going around, going around, and finally bring it out, so that we create effectively n number of loops. So the number of times we'd run that wire around, for each time we run it around, we create an effective new loop. And we can multiply this number, we can multiply out the front of this term, the n term, which can really increase the voltage.